Okay, so today we're going to talk about simplifying radicals. And I don't just mean taking square roots, I mean actually simplifying what's happening inside. So there's a few definitions we need to talk about first. First thing, the radical sign, which is a symbol, looks like this. That indicates that the principal or non-negative root of an expression. Then we have the radicand. That's the expression under the sign. A radical expression is just an expression that contains a radical. A radical expression is in simplest form when there's no radicands that have a perfect square factor other than 1. Also, no radicans contain fractions, and no radicals appear in the denominators of fractions. So like I said, this is more than just taking the square root like we've done before. Okay. Just a couple of things we're going to do as we simplify our radicals. One of them is called the product property of square roots. So if we said that number A and number B and A and B both have to be greater than 0, where we can say that the square root of A times B is equal to the square root of A times the square root of B. So what do I mean when I say this? We're going to use prime factorization and the product property to simplify our radicals. Remember prime factorization? Sometimes we use trees, sometimes we just wrote things down, but all of that was dealing with this. So for example, let's say we have the square root of 18. Square root of 18, if we find the prime factorization, we can say that it's 2 times 3 times 3. Remember, 3 times 3 is 9, times 2, that gives you 18. So here is prime factorization. Then we're going to break it up into the product property. Square root of 2 times the square root of 3 times 3. I'm going to rewrite that. Square root of 2 times square root of 9. That's just showing you what our remaining perfect square is. So then I'm going to go ahead and take my square root of 9 and rewrite this as 3. I'm getting rid of my radical. So now I have the square root of 2 times 3. I'm going to rewrite it this way. Remember, the commutative property tells us that we can flip-flop multiplication. Also works for addition, but we're only doing it with multiplication today. I want to put my number without the radical in front every time. So I'm going to say 3 square roots of 2. So the square root of 18, when simplified, is equal to 3 square roots of 2. So even though I still have a radical in my answer, this is as simplified as I can get without using a calculator. Because obviously you could take a calculator and find the square root of 18, and it's going to be 3 point something. This is what I want when I say simplify a radical. Okay, so let's do some examples. Okay, here's 2 different ways you can do it. Down here I use the product property. Up here I just did prime factorization. So let's look at all of these. They're all already done, but you need to copy all of them down. So number 1, took 147. Now, these problems are where you're really going to need to know your factors. So 147 is equal to 3 times 49. So I broke it down. Look, here I've got my factor trees going. 3 times 7 times 7. Okay, well, 7 times 7, that's a perfect square. So I've rewritten it here as square root of 3 times the square root of 49. I went ahead and got rid of my radical and brought out my 7. Notice again, just like in the one before, I put my non-radical number in front so that I said my answer is 7 square roots of 3. No calculator is needed, provided you can figure out what your factors of 147 are. Let's look at the next one, 605. Well, 605 is 5 times 121, so I broke it down. 5 times 11 times 11. Square root of 5 times the square root of 121. I dropped my radical, and I now have 11 times 5. If you don't need to show this step, that's fine. You can go straight here. Okay, what about square root of 75? Everybody should be able to do this one pretty easily. 3 times 5 times 5, or square root of 3 times the square root of 25. 25 is a perfect square, so out it comes. Okay, what about using the product property? Now the nice thing about the product property is that because we were going to involve the commutative property, it tells us we can start moving numbers around under the radical sign. So like here, I said square root of 5 times the square root of 35. Well, when I first look at this, I have square root of 5 times square root of 5 times 7. When I'm looking at it this way, I have no perfect squares. What am I going to pull out? So I'm going to move this 5 from the 5 times 7 over here by this 5. Well, voila, I now have square root of 5 times 5. There's my perfect square. Remember, a perfect square is simply two numbers multiplied together. So now I can throw away this radical and just bring out my 5, and my answer becomes 5 square roots of 7. I never even started with a big whole number. Okay, what about this one? Square root of 6 times square root of 60. If I started with that actual whole number, I'm looking at 360, or square root of 360. Okay, once again, I have no perfect squares under my radical at this time. I'm looking at square root of 2 times 3, and over here, square root of 2 times 2 times 3 times 5. So I've got to do some moving around, and I kind of chunked it up into two number pieces. I have the square root of 2 times 2 times the square root of 3 times 3 times the square root of 5 times 2. In this case, I have two perfect squares, so I brought them both down. 2, 3, 5 times 2 isn't a perfect square, so I put it back together as the square root of 10. So for my final answer, I'm going to multiply my two perfect squares together. 2 times 3 gave me 6. I left the square root of 10 as it was. You really like to get it down to a prime number, but when it's not going to happen, just leave it as small as possible. If a prime is not possible, then it just can't happen. Try and get it as small as you can. Okay, so these are some simple examples. Sometimes, though, your numbers are in division. Sometimes they're divided. Well, if they start out in a divided way, then you still work them the same way. But before you can divide, or before you can use your product property or your prime factorization, you have to simplify. So here we have square root of 88 over square root of 11. This is the same as saying this. Okay. Problem is, neither square root of 88 nor square root of 11 are perfect squares. So what can we do? We can simplify this. 88 is divisible by 11. It's 8. So now I have square root of 8. Well, I can divide that up. 8 happens to be 2 times 2 times 2. 2 times 2 times 2. Well, 2 times 2 is 4. So now I'm dealing with square root of 2, or excuse me, square root of 4 times square root of 2, which breaks down into 2 square roots of 2. A very nice, simplifiable radical. So then we look at this one. Square root of 12 over 27. Well, that's really major fractions, which again, could be written like this. If a number is written like this, you can rewrite it with one large radical, just like if it has one large radical, you can write it with 2. Well, this simplifies to become square root of 4 over 9. I'm going to rewrite it with my 2 radicals. Well, that's 2 perfect squares. So I'm going to take both perfect squares and take the square root of them, which you already know how to do. So square root of 4 is 2, square root of 9 is 3. I've gone from this ugly problem of square root of 12/27 to 2/3 in just a few simple steps. Okay, what about this last one? Square root of 90 over 5. Well, 90 ends in a 0, which means it's divisible by 5. If you think back to those divisibility rules you've learned somewhere along the way. 90 divided by 5 is 18. I still have my square root symbol. So I'm looking at the square root of 18, which is much better than 90 over 5. The square root of 18, when you break it down, becomes 2 times 3 times 3. If you remember, it's the number we started with in our notes. So I'm looking at square root of 2 times square root of 3 times 3, which breaks down into 3 square roots of 2. And that is how you simplify radicals.